What if the single most important discovery in human history wasn't made on Earth but in the cold black vacuum of space near Mars? What if a messenger arrived carrying secrets not from our past but from a star system light years away? On October 3rd, 25, that what if became our new reality. Something has just flown past the red planet. It's not one of our spacecraft. It's not an asteroid captured from our own solar system. It is a wanderer, a traveller, a refugee from an entirely different solar system captained by a completely different sun. And it is glowing a ghostly, impossible, brilliant green. Scientists have scrambled to give it a name, 3i Atlas. That simple I in its name stands for interstellar, and it is the key to everything. This isn't just a rock, it's a message in a bottle thrown into the cosmic ocean billions of years ago. And we are the first civilization to ever read it. As 3 Atlas made its closest approach to Mars, the army of orbiters we sent to study the Red Planet missions from NASA, from Europe, from the UAE, all turned their electronic eyes away from the Martian surface and toward this new unexpected guest. What they saw has already begun to rewrite our understanding of the universe. The chemistry was all wrong. The light signature the object gave off its spectrum was bizarre. Think of a spectrum as a chemical fingerprint. It's how astronomers read the ingredients of a star or a planet from millions of miles away. The fingerprint of 3i Atlas showed a combination of materials we simply do not see in our own comets. It was rich in nickel, a heavy metal that hints at a violent high-temperature past. But the real shock was the overwhelming glow of something scientists call diatomic carbon, that is 2 carbon atoms bonded together. This specific carbon molecule is what's responsible for its eerie green glow. This green isn't just for show, it's a chemical reaction, a signal flare telling us this object is loaded with the single most important element for life as we know it. But it wasn't just what it was made of, it was where it was going and how fast it was getting there. Its path, its orbit made no sense. It was moving at a speed that our sun's gravity simply cannot control. It was like seeing a speedboat fly across a quiet fishing pond. The data was immediate, and it was undeniable this object does not belong to us. It is an immigrant from deep space. This single green glowing rock has ignited a firestorm in the scientific community, and in this video we are going to unpack this incredible story. You are going to find out exactly how this impossible visitor was found, spotted by a robotic system on Earth that was designed to protect us from Earth-killer asteroids. We will dive deep into that strange green light and explore why this specific chemical soup rich in carbon and exotic metals points directly to the building blocks of life, what we call prebiotic chemistry. We are going to look at the stunning, beautiful mathematics of its orbit, the cosmic fingerprint that proves beyond any shadow of a doubt that this rock began its journey hundreds, perhaps thousands of light years away around a completely different star. And finally, we will discuss why 3 Atlas is already shaping up to be a far more important discovery than Oumuamua, that first mysterious visitor from 2017. The story of 3 Atlas isn't just about spotting a visitor. It's about catching it, studying it, and unlocking the secrets it has carried for untold eons across the dark emptiness of the galaxy. So how do you find a needle in a cosmic haystack that stretches for light years? The story of the discovery begins not in the deep space of Mars, but on Earth. It begins on a volcanic mountain in Hawaii, at a facility called the Atlas Observatory. Atlas stands for the Asteroid Terrestrial Impact Last Alert System. Its job is simple and it's terrifying. It scans the entire night sky over and over again every single night. It's looking for anything that moves. Its primary mission is to find asteroids on a collision course with Earth to give us that last alert before a potential impact. It is quite literally an Earth killer hunter. On a routine night, the Atlas system got a ping. This isn't an audible sound, of course, but a digital flag in the data. The automated telescopes had taken a series of images of one patch of sky, and the software detected a faint dot of light that was moving against the background of fixed distant stars. This happens thousands even of times a night. That's what asteroids and comets do. But the computers immediately flag this one. The software designed to calculate an object's orbit in mere seconds sounded an internal alarm. This object was moving fast. It was moving far too fast to be a resident of our quiet solar system. It wasn't just breaking the local speed limit, it was moving with a velocity that suggested it was completely ignoring the sun's gravity. Imagine being the young astronomer on duty who gets that alert. You run the numbers again, and then you see it. The key, the whole story of this object kit was told in a single number, its orbital eccentricity. Now that sounds complicated, but the idea is actually very simple. In our solar system, an object with a perfectly circular orbit like the Earth almost has an eccentricity of 0. An object in a long stretched out oval like Halley's comet has an eccentricity between 0 and 1. That number 1 is the magic wall. It is the gravitational fence of our solar system. Anything with an eccentricity below 1 is trapped by the Sun's gravity. It's one of us. It has to keep coming back. The orbit for 3i Atlas was calculated. Its eccentricity was 1.0037. That tiny number that 0.0037 after the 1 is the most important part of this entire story. It is the mathematical proof, the unambiguous, undeniable fingerprint that this object is not in orbit around our Sun. It is not one of us. An eccentricity greater than 1 means it is on an escape trajectory. It's a one-way ticket. It has flown in from interstellar space. It will loop once around our Sun and it will fly right back out into the darkness, never to return. This was the moment we knew we had another interstellar visitor. We have been here before, but not like this. In 2017, the world was stunned by the discovery of Oumuamua, the first interstellar object we ever identified. It was a complete mystery. It was bizarre, shaped perhaps like a cigar or a flat pancake, and it wasn't glowing at all. We only spotted it as it was leaving a faint tiny dot racing away from us. We barely got a good look. We were left with more questions than answers. Was it a comet, an asteroid? Was it, as some scientists boldly suggested, an alien probe? We still don't really know. Then in 2019 we found 2i Borisov. This one looked more familiar. It was clearly a comet with a bright tail of gas and dust. We got a better look at Borisov, but it was still far away. We studied it from a distance, like watching a fascinating stranger from across the street. But 3i Atlas, this is different. This is the moment history will remember. Oumuamua was a mystery we saw only in our rearview mirror. Borisov was a guest we waved to from the porch. 3i Atlas is a guest we have invited into our living room. Because of its orbital path and because of pure dumb luck, it flew close to Mars, where our most advanced scientific instruments were already waiting. We didn't just see it with Earth-based telescopes. We got to study it up close and personal with high-resolution cameras and spectrometers on our Mars orbiters. We have the data. We have the spectra. We have the chemical breakdown of a piece of another solar system. Oumuamua and Borisov were the appetizers. 3i Atlas is the main course. And what it's telling us is already changing how we think about the universe, our place in it, and the very origin of life itself. As 3i Atlas fell toward our Sun, its journey through the physical emptiness of space was over. It had entered the functional part of our solar system, the part where the Sun's power begins to matter. The Sun's ancient relentless breath, the solar wind, and its even more powerful light began to peel back the layers of this visitor, performing a long-distance autopsy on a body that was still very much alive and reacting. For astronomers, this is the moment of truth. A comet is a closed book while it is frozen in the dark. But as it nears a star, it opens. The ice turns to gas, the dust streams away, and in that cloud of gas and dust, the coma is the story. It is the chemical fingerprint, the ingredients list of the place it was born. When we pointed our best instruments at 3i Atlas, we expected to see the familiar story of a comet. We expected water, carbon dioxide, maybe some ammonia. We were prepared for the basics. What we were not prepared for was a chemical signature so bizarre, so contradictory, and so utterly alien that it forced us to rewrite our assumptions about how chemistry even works in the cold darkness between the stars. The object's trajectory told us where it came from, but its chemical analysis began to tell us what it was, and that it turned out was the far greater mystery. Mystery 1, the green light. The first clue that 3i Atlas was no ordinary visitor was its colour. As the coma, the fuzzy atmosphere surrounding the icy nucleus grew, it began to glow. This is normal. The Sun's energy excites the gases, causing them to fluoresce, to shine with their own light, just like a neon sign. But it was the colour that captivated everyone. It was not white or blue. It was green, a deep shimmering, almost artificial-looking emerald green. It was a ghostly halo that made the object look less like a natural comet and more like a celestial phantom. This vibrant green aura was beautiful. But to a scientist, beauty is often a sign of a specific chemical process. And in the world of comets, a green glow means one thing and one thing only: carbon. Specifically, the glow comes from a molecule called diatomic carbon, or C2. This is a simple molecule made of just 2 carbon atoms bonded together. It is not something you find lying around on Earth. It is highly unstable in our atmosphere. But in the vacuum of space, it is a common component of comets. The process is a simple, elegant chain of events. The comet's ice, which is laced with more complex carbon-based molecules like acetylene or methane, gets blasted by the sun's powerful ultraviolet radiation. This ultraviolet light acts like a molecular hammer, shattering the larger, more stable molecules. In the debris of that collision, you get fragments. One of those fragments is diatomic carbon. This newly freed molecule is then struck again by sunlight, which gives it a jolt of energy. The molecule does not like this. It wants to be calm. To release that extra energy, it emits a photon, a particle of light. And it just so happens that when diatomic carbon releases its energy, that photon has the precise wavelength that our eyes and cameras register as a brilliant emerald green. So mystery solved? Not at all. The problem was not that it was green. The problem was how green it was. As we measured the brightness of this green light, the numbers did not make sense. They were, to put it mildly, impossible. 3I Atlas was glowing with an intensity that was 3 times stronger than any comet we have ever observed coming from our own Oort cloud. Let us be very clear. This was not a small measurement error. It was not 10 or 20% off. It was 300% brighter in this specific green wavelength than the theoretical maximum we thought was possible for an object of its size and distance. This presented a profound problem. Where was all this diatomic carbon coming from? Was 3I Atlas made of fundamentally different stuff? Did it contain a vastly richer supply of the parent molecules that break down to create the green glow? If so, this would mean the interstellar cloud it formed in somewhere far away had a completely different chemical makeup than our own. Or was the mechanism itself different? Was something else happening? Perhaps the object was not just a single nucleus, but had already shattered into a cloud of smaller icy fragments, exposing a much larger surface area to the sun's radiation. This fragmentation hypothesis was popular, but it did not fully explain the sheer efficiency of the green light's production. It was as if this comet knew a secret, a chemical trick to produce this glow that our own comets had never learned. The eerie green light of 3I Atlas was a warning shot. It was the universe telling us that our rulebook, the one we wrote by studying the comets in our own backyard, was about to be thrown out. The object was not just passing through, it was actively challenging our understanding of what a comet is, and the green light was only the beginning. The strangest clue was yet to come. Mystery 2, the strange nickel vapor. If the green light was a puzzle, the next discovery was a paradox. It was something that should not exist. While astronomers on Earth were studying the object's light, a different set of eyes was also watching, though by accident. The European Space Agency, or ESA, has an orbiter around Mars called the Trace Gas Orbiter, or TGO. Its job is to sniff the thin Martian atmosphere looking for tiny trace amounts of gases, like methane, which could be a sign of life or geological activity. It was not designed to look at comets. But as 3I Atlas cruised through the solar system, it happened to pass relatively close to Mars's orbit. The TGO team, in a moment of brilliant opportunism, decided to point their highly sensitive instruments away from Mars and toward this new visitor. What they found has sent a shockwave through the fields of astrophysics and chemistry. The TGO detected metal, not just grains of metallic dust, which is common, but gaseous vaporized metal. And not just any metal, they found nickel vapor. To understand why this is so stunning, you need to understand 2 things: what nickel is and where 3I Atlas was. Nickel is a heavy, durable metal. It is what we use to make stainless steel and coins. Like all metals, it has an incredibly high boiling point. To turn a solid block of nickel into a gas, you need to heat it to over 2,700 degrees Celsius, or nearly 5,000 degrees Fahrenheit. You essentially need the surface of a star or a blast furnace. Now, where was 3I Atlas when this discovery was made? It was far from the Sun. It was well outside the orbit of Mars, more than 300 million kilometers from our star. At that vast distance, the Sun is a bright light, but its heat is weak. The surface temperature of 3I Atlas was estimated to be frigid, likely around -70 degrees Celsius or -94 Fahrenheit. This is the central impossible fact. We found a gas that requires thousands of degrees of heat, and we found it in a place that was dozens of degrees below freezing. It is like finding a cloud of steam rising from a block of Antarctic ice. It is not a puzzle, it is a physical contradiction. So what could possibly be happening? Nickel itself cannot sublimate, turn from a solid to a gas in the deep cold. It is a physical impossibility. Therefore, the nickel must not have been pure nickel. It must have been hiding inside a different, much more fragile molecule. This is where the brilliant hypothesis from the University of Liège in Belgium comes in. They proposed that the nickel was not travelling as a pure metal, but was locked in a strange exotic chemical bond. They suggested it was part of a molecule called nickel carbonyl. This is not a molecule we talk about in everyday life, and for good reason. It is a strange compound where a single nickel atom is bonded to 4 carbon monoxide molecules. Think of it as the nickel atom being held in a cage of carbon monoxide. This exotic molecule has a very specific and very important property. It is incredibly unstable and fragile. It does not care about the 200-degree boiling point of nickel. It only cares about its own flimsy bonds. A nickel carbonyl breaks apart, it decomposes and releases its nickel atom at a temperature of just -20 degrees Celsius or -4 Fahrenheit. Suddenly the paradox has a solution. 3I Atlas was not a lump of hot metal. It was a frozen snowball carrying a chemical bomb. In the deep interstellar cold at -200 degrees or more, the nickel carbonyl was perfectly stunned, frozen into this comet's ice. But as the comet crossed the solar system and passed the orbit of Mars, its temperature climbed. It crossed the thaw point. It warmed up past -70, past -50, past -30, and then it hit -20 degrees Celsius. At that exact moment, the nickel carbonyl molecules all over the comet's surface broke apart. The carbon monoxide cage shattered and the nickel atoms were released instantly, becoming a gas. The trace gas orbiter did not detect a metal boiling. It detected the coordinated chemical release from a cosmic transporter. This is the exotic chemistry we had never seen before. This implies that the dark cold clouds between the stars are not just simple factories for water and carbon dioxide. They are dark chemistry labs capable of building complex and unstable molecules like nickel carbonyl molecules we did not think could exist naturally in space. This discovery changes everything. It suggests that comets and asteroids are not just delivering water and simple organic soot to planets. They could be delivering metals, and if they can deliver nickel, what else? Iron, magnesium. These are the fundamental building blocks of a planet's core, the very ingredients needed for geology, and perhaps for life. I-Atlas showed us that these interstellar messengers are not just carrying water, they are chemical delivery systems of astonishing complexity. They are sowing the seeds of chemistry itself, sprinkling the galaxy with complex ready-made ingredients that can kickstart the processes of planet formation and just maybe the origin of life itself. The story of our encounter with 3 on the Atlas truly began on September 12, 25. On that day, a new fast-moving pinprick of light was officially logged by the Minor Planet Center, confirming its interstellar origin. It was real, and it was heading our way. Immediately, the great eyes of Earth turned toward it. The Hubble Space Telescope adjusted its gaze, straining to see the visitor. In the deserts of Chile, the Very Large Telescope VLT array activated its adaptive optics, attempting to cancel out the blurring effect of our own atmosphere to get a clear look. But there was a problem. From Earth, even with our best instruments, through our atlas was just a faint smudge, a rapidly moving point of light against the black. We were trying to study a complex alien object from over 100 million kilometers away. It was, as one astronomer described it, like trying to study the flight path of a single distant firefly on a very dark night. You might see that it is there, but you cannot see its wings, its color, or how it moves. The data was sparse and our understanding was frustratingly incomplete, but then humanity realized it had an ace up its sleeve. We weren't just on Earth. For the first time in history, when an interstellar guest arrived, we had eyes somewhere else. We had front row seats. The orbital path of 3I Atlas was calculated to take it screaming past the planet Mars at a cosmically close distance. And orbiting Mars, we had our robotic ambassadors, the Mars Reconnaissance Orbiter MRO and the ExoMars Trace Gas Orbiter TGO. This was the gold mine. This was the breakthrough. If watching from Earth was like observing that distant blurry firefly, watching from the Mars orbiters was like having a high-speed, high-definition camera mounted just a few feet away from the object as it sped past. The data wasn't a trickle, it was a flood. As 3I Atlas passed Mars, our orbiters didn't just look, they stared. They mapped it in thermal infrared, scanned it with radar, and captured it with resolutions we could have only dreamed of from Earth. And for the first time, we had a true physical portrait of 3 Atlas. So what did this high-speed camera show us? What is this traveller physically? The first surprise was its size. It was small. In cosmic terms, it was almost tiny. Based on its brightness and the data from the flyby, we confirmed its longest axis was only about 800 meters. This isn't a planet killer. It's a city block killer. This is an object you could in theory walk across in about 10 minutes. Its small size, however, only made its other properties even more baffling. The most profound discovery from the Mars flyby was its structure. 3I Atlas is not a single solid piece of rock like an asteroid. It is not a solid chunk of ice like a comet. Instead, the data painted a clear picture of what astronomers call a rubble pile. It is a loose collection of boulders, gravel, ice, and dust all held together precariously by their own very weak shared gravity. Imagine taking a large bag of different sized rocks and sand, shaking it up, and then magically removing the bag, leaving the contents floating in space. That is 3I Atlas. It's not a boulder, it's a floating gravel bank. This structure means it is fragile. It is a cosmic survivor, but it is not solid. This rubble pile nature made its rotation all the more dramatic. Our Mars observations timed it perfectly. It completes one full turn every 4.2 hours. This is incredibly fast for an object so loosely held together. It is spinning near the structural limit of what a rubble pile can handle before it tears itself apart, slinging its constituent pieces out into space. And it wasn't a clean spin. The object was tumbling. It had a pronounced wobble, what scientists call a complex rotation. It wasn't just spinning on one axis like a well-thrown football. It was spinning and tumbling end over end simultaneously like a football that's been kicked badly. This tumbling motion suggested it had a recent violent history. Perhaps a collision in its home system, or even on its long journey here, had set it tumbling through the dark. But the team analysing the rotation found the biggest shock of all. The wobble was one thing, but the rotation speed itself was not constant. It was changing. 3I Atlas was speeding up. In the cold, empty vacuum of space, objects don't just speed up on their own. The laws of physics, specifically the conservation of angular momentum, forbid it. This isn't like a car pressing the accelerator. Something was applying a torque, a twisting force to this 800-meter wide pile of rubble. What could it be? The leading hypothesis, and the one that opened a whole new chapter of study, was asymmetric jets. As 3I Atlas got closer to the Sun, the faint warmth was enough to heat ices trapped inside its porous rubble pile structure. This ice wouldn't melt. It would sublimate, turning directly from a solid into a gas. This gas trapped beneath the surface would build up pressure and then burst out into space through cracks and fissures. If these jets were perfectly balanced, one on each side, they would cancel each other out. But if they were asymmetric, if one jet was stronger, or if they were pointing in slightly different directions, they would act like tiny misplaced rocket thrusters. Over time, these tiny uneven pushes would spin the object up faster and faster like a pinwheel in the wind. Another more exotic idea was also proposed. Could radiation from elements inside the object decaying radioactively be heating one side more than another? This heat radiating away unevenly could create a tiny push. We see this effect in our own solar system. But the acceleration of 3I Atlas seemed too strong for that alone. The jets seemed to be the key. This theory of jets gained massive support from the MOVANG, the gold mine of MRO, specifically from its most powerful camera, HiRISE, which stands for High Resolution Imaging Science Experiment. HiRISE wasn't just taking pictures of the object, it was analysing the environment around 3I Atlas, and it found dust, but not just any dust. It detected distinct particles, tiny grains of material being ejected from the object, and it could even measure their speed. It found they were being pushed away at high velocity. These were the smoking guns. These particles were being carried away by the invisible jets of gas. But it was the kind of dust that told the real story. When scientists analysed the debris field, they found what they called a bimodal size distribution. This is a technical term for a simple, fascinating idea. The dust wasn't all one size, it came in two distinct flavours. On one hand, there was a cloud of incredibly fine powder. These were microscopic grains, the kind of fine dust you'd expect from ice vaporising violently into space, carrying tiny bits of soot and ancient carbon molecules with it. This was the comet part of its personality. But on the other hand, HiRISE and the other instruments detected much larger pieces. They found gravel-sized fragments. Chunks the size of pebbles or even small marbles were being thrown clear of the main body. This was not typical comet behaviour. This was something different. So let's recap this bizarre portrait. We have a small 800-metre object. It's not a solid rock, but a fragile rubble pile. It's spinning fast every 4.2 hours. It's wobbling as it spins. It is speeding up, likely due to asymmetric jets. And these jets are throwing off not just fine powder, but also chunks of gravel. What does this tell us? Where did this traveller come from? The bimodal dust distribution is a huge clue. It strongly suggests that 3I Atlas was formed in a chaotic protoplanetary disk, a place of violence and collision. This isn't an object that formed peacefully in the quiet outer reaches of its star system. This mixture of fine powder, primordial dust, and heavier gravel processed smashed-up rock points to a young solar system where planets were just beginning to form, smashing into each other, grinding down mountains into pebbles and pebbles into dust, all in the same region. Alternatively, 3i Atlas might be a fragment of a much larger differentiated parent body. Imagine a young small planet in another solar system, a body that was large enough that it had already separated into a dense rocky core and a lighter icy crust. A catastrophic collision with another forming planet could have shattered this young world. 3i Atlas. This tumbling pile of rubble could be a piece of that shattered boundary layer, a mix of the crust and the core blasted into interstellar space. This would explain the mix of materials, the rubble pile structure, the result of being blasted apart and then slowly pulling itself back together by gravity and its violent tumble. And this brings us to the final, almost poetic aspect of this encounter. The timing, the sheer beautiful coincidence of it all. This object, this messenger from another star, didn't visit us in 1950 when we could only look through basic telescopes and wonder. It didn't wait until 2150 when perhaps our Mars orbiters might be decommissioned and our attention elsewhere. No 3i Atlas arrived at a unique moment in human history. Its appearance, its flyby of Mars, coincided perfectly with a new golden age of astronomical preparation. Just as this interstellar messenger was making its closest pass, humanity was on the verge of launching its next generation of cosmic explorers. We were finalizing the Interstellar Mapping and Acceleration Probe, or IMAP. This is a mission specifically designed to study the particles streaming in from interstellar space to understand the wind that blows between the stars. 3i Atlas, by ejecting its own sample of interstellar dust right into our backyard, gave IMAP a ground truth target before it even launched. On the ground, the Vera Rubin Observatory in Chile was preparing for first light. This is a revolutionary new telescope and observatory designed to scan the entire night sky every few nights to find exactly these kinds of fast-moving, transient or unusual objects. 3i Atlas was in a way the universe's way of saying, "You're building the right tool, here is a test run, here is exactly the kind of thing you are looking for." It felt scripted. It felt like a calibration, a test given to us by the cosmos. We had built the cameras, the orbiters, the new telescopes, and right on cue the universe sent us the most spectacular, complex and mysterious subject we could have asked for. The Mars flyby didn't just give us a portrait of 3i Atlas. It held up a mirror showing us that we were finally ready to look. To find the origin of 3i Atlas, astronomers had to become cosmic detectives. The object itself was the primary witness, and it carried all the clues. The investigation wasn't about what it was anymore. They knew it was a cosmic tarball, a fundamentally alien object. The case now was to find out where it came from and who or what had sent it. The entire investigation rested on following the evidence, and the evidence pointed to a violent ejection from a star system completely unlike our own. The most critical piece of evidence was the object's trajectory, its velocity vector. This is the cosmic equivalent of a fingerprint. It tells us not just how fast something is moving, but in what direction. 3i Atlas was clocked at a speed of 26.3 kilometers per second. This incredible speed was the smoking gun that proved it was an interstellar visitor. It was moving far too fast for our sun's gravity to have ever captured it. It was just passing through. By knowing this exact speed and direction, detectives, in this case astrophysicists, could perform a kind of forensic analysis. Using powerful computers, they ran n-body simulations. This is a fancy term for a simple idea rewinding the tape. They created a digital map of our section of the galaxy, input the object's current path, and calculated the gravitational pull of every known star backward in time. They were in effect watching the object's journey in reverse to see where it started. The simulation didn't point to a random patch of sky, it pointed to a specific neighbourhood, the Perseus arm. Our Sun is in a smaller spiral arm of the Milky Way, but the Perseus arm is the next major one outward. The computer models showed the object had crossed the vast empty space between these arms, and its journey had begun somewhere in a cluster of stars between 150 and 200 light-years away. The search was narrowed from the entire galaxy to our own backyard. With the location identified, the detectives started looking for suspects. They needed to find a star system that had the motive and the means to eject a planetary body. The means would almost certainly be a giant planet, a Jupiter, which could act as a gravitational slingshot. A prime suspect was quickly identified, the star HD 28185. This star was a perfect match for the profile. First, it is a sun-like star, so it was known to form planets. Second, and most importantly, it has a known Jupiter-sized gas giant. This was the weapon they were looking for. This system, located in the correct direction, had both the building blocks for a body like 3i Atlas, and the giant planet needed to violently fling it into interstellar space. The case seemed almost closed, but in any good investigation you have to check the details, and the details didn't quite line up. There was a small velocity mismatch. When they ran the simulation perfectly from HD 28185, the final vector didn't exactly match the one they measured for 3i Atlas. It was close but not a perfect hit. This alibi meant that while HD 28185 was a good candidate, it might not be the culprit. The investigation had to be widened. Other suspects were considered. One was Gliese 687, a red dwarf star. Statistically, this was a good bet, as red dwarfs are the most common stars in the galaxy, but the chemical forensics ruled it out immediately. 3i Atlas was famous for its blue glow, a sign of a carbon-rich body. Gliese 687 is known to be carbon-poor. The DNA didn't match. The object could not have been built from the materials available in that system. This led to a new, more compelling theory. What if 3i Atlas didn't come from a single isolated suspect like our solar system? What if it came from a rough neighbourhood, a place far more chaotic? This new suspect was a dense star cluster. Imagine a stellar nursery, a place where hundreds of stars are born at the same time, all crowded together. This environment is the perfect scene of the crime. With so many stars and so many new giant planets all pulling on each other, gravitational ejections wouldn't be rare. They would be common. This dense cluster theory also solved another key mystery: the object's strange chemical makeup. Analysis of its dust revealed a nickel-to-iron ratio that was 3.2 times higher than our Sun's. This was a major anomaly. Where did all that extra nickel come from? A dense cluster provides the answer. These clusters don't just have sun-like stars. They have massive giant stars that live fast and die young in massive explosions called supernovae. These supernovae pollute the surrounding gas clouds with heavy elements they've created, including nickel. If 3i Atlas formed from a gas cloud that had been seeded by a nearby supernova, it would naturally have this strange high nickel ratio. The evidence was lining up. With a strong theory for where, a dense cluster in the Perseus arm, and how ejection by a giant planet from a cloud polluted by a supernova, the final question was when. How long ago did this happen? To figure this out, scientists used cosmic ray exposure dating. For its entire journey, 3i Atlas was unprotected, flying through the open ocean of interstellar space. This space is filled with high-energy cosmic rays that blast everything they touch. By measuring the damage or tan these rays left on the object's surface materials, scientists could estimate how long it had been exposed. The calculations showed it had been drifting for 5 to 15 million years. It was a true cosmic castaway wandering the void for millions of years, before it finally by pure chance stumbled into our solar system. This all connects back to the very first clue, the strange blue light. That light, the powerful glow of C2 diatomic carbon, was the object's confession. It was telling us from the very beginning that it was not from around here. It was born in a place where carbon compounds were the dominant building material, not water ice. The James Webb Space Telescope, JWST, provided the final conclusive report. Its powerful infrared instruments analysed the dust from 3i Atlas and confirmed the cosmic tarball theory beyond all doubt. It found the object was made of a 1:4 ratio of silicates rock to organic carbon-based material. This is the complete inverse of comets from our own solar system, which are mostly rock and ice with only a small fraction of organic material. The case was solved. 3i Atlas was an alien born in a carbon-rich star cluster, chemically enriched by an exploding star and violently ejected by a giant planet, only to drift for millions of years as a dark tar-like orphan before its brief glowing visit to our Sun. When the data from this strange interstellar visitor first streamed back to Earth, the feeling in the astronomical community was one of pure excitement. But that excitement quickly turned to confusion and then to a deep, profound and fascinating disagreement. This object, our first clear visitor from another star, was not behaving like anything we knew. It was supposed to be simple. In our solar system, almost every small object is either a rocky asteroid, a dry, dusty chunk of leftover planetary material, or an icy comet, a dirty snowball from the cold outer darkness. We expected our visitor to be one of these. It was not. The data was a mess of contradictions. The first problem was its acceleration. The object was speeding up as it moved away from our sun, as if a tiny invisible engine was giving it a gentle push. Comets do this all the time. As the sun heats them, their ice turns to gas shooting out in jets. This process, called sublimation, acts like a small rocket pushing the comet. But to do this you need a tail, a visible cloud of gas and dust called a coma. This visitor had none, or if it did, the amount of gas was so small that it could not possibly explain the push it was getting. Then there was the chemistry. Our telescopes can read the chemical fingerprints of the dust and gas coming off an object. We expected to see water, the main ingredient of our own comets. We did not. Instead, we found a strange brew. There were hints of carbon-rich molecules like acetylene, a welding gas, and in one famous disputed reading there was a whisper of nickel, but in a strange form. Some suggested it could be nickel carbonyl, a compound of nickel and carbon monoxide. This was bizarre. Our comets are not rich in nickel carbonyl. And then there was the dust. The grains of dust it left behind were unusual. They were fluffy and porous, but their composition was not quite right. This collection of contradictory data, the acceleration of a comet, but the appearance of a rock and a chemical signature from another world, shattered the community's easy consensus. The data simply did not fit our simple models. It was like finding a boat that could sail on water, but had no hull, or a bird that could fly with no wings. This is where the Great Divide began, a split that defines the entire story of this object. It is a fundamental argument about the nature of science itself. On one side you have the camp of continuity. These are the scientists who believe that our current understanding of physics and astronomy is complete enough to explain the visitor. They argue that the object is strange, yes, but it is not magical. It must be a natural object that simply belongs to a class we have not seen before. Its properties can be explained by known if unusual chemistry and physics. The challenge for them is to find the right combination of known processes that fits all the facts. On the other side, you have the camp of discontinuity. These scientists look at the same data and come to a different conclusion. They argue that the data is so bizarre, so far outside our established models, that we might be looking at something truly new. This could mean a new class of astronomical object that our theories never predicted, or it could mean we are witnessing a phenomenon we do not understand, and for a very small, very vocal minority, it could even mean something artificial. The debate then is this just the weirdest comet we have ever seen, or is it the first hint that the galaxy is more strange and complex than our textbooks told us? Let's explore the competing theories that grew out of this division, starting with the most mainstream. Theory number 1. The leading orthodox explanation is that the visitor was an exotic carbon-rich comet from another star's Oort cloud. This is the champion of the continuity camp. It tries to explain all the weirdness using physics we already know. The theory goes like this: the object was in fact a comet, but it was not a water ice comet like we are used to. It came from a different solar system, one where the chemistry of its outer cloud was different from ours. This comet, the theory holds, was rich in other kinds of ice, specifically frozen gases like acetylene or perhaps solid carbon monoxide. These substances turn to gas sublimate at much lower temperatures than water. This is a key point. This exocomet could have been active, shooting out jets of gas long before it reached our sun, while it was still in the cold deep space where we first spotted it. This would explain why it did not seem to be shedding much material when it got close to our sun. Maybe its most volatile gases were already gone. But what about the acceleration? The proponents of this theory have a clever answer. They suggest a symmetric sublimation. This means the gas jets were not firing randomly. Instead, perhaps only one side of the object was being heated and releasing gas, or the gas was being channeled through a specific vent. This would act like a single steady rocket engine pushing the object and causing it to accelerate. Because the gas was something like carbon monoxide, which is hard to see from Earth, it would create an invisible tail. This neatly explains the acceleration without a coma problem, and the nickel. This is where the theory gets even more specific. The idea of nickel carbonyl is central. This compound, 1 atom of nickel to 4 of carbon monoxide, is a gas at room temperature but would be frozen solid in deep space. If the comet was full of this stuff, it would sublimate as it warmed up. The sunlight would then break the nickel carbonyl apart, releasing the nickel atoms, which our telescopes would briefly detect, and the carbon monoxide, which would be invisible. This would perfectly explain the strange nickel signal. This entire theory is a beautiful piece of scientific problem solving. It takes all the strange data points, the acceleration, the lack of water, the nickel and weaves them into a single coherent story using known chemistry. It just asks us to accept that comets from other stars can be chemically very different from our own. However, this explanation does not satisfy everyone. For some, it feels too complicated. It requires a Goldilocks object, one with just the right amount of acetylene, just the right amount of nickel carbonyl, and just the right shape to create asymmetric jets. When a theory requires that many just right conditions, it starts to make some scientists nervous. This led to theory number 2, the main challenger, which is both more violent and in some ways more elegant. This hypothesis, championed by the brilliant theorist Konstantin Batygin, is that the visitor was not a comet at all. It was a fragment of a shattered exomoon. This is a much more dramatic idea. Imagine in a solar system light years away a giant planet like Jupiter or Neptune. Around this planet orbits a large moon, one big enough to be differentiated. Meaning like Earth, it has a heavy metallic core and a lighter rocky icy crust. Now imagine a chaotic event. Perhaps another planet passes too close or the system is unstable. This large moon is gravitationally disturbed. Its orbit changes and it begins to spiral inward, too close to its massive parent planet. When it crosses a certain boundary called the Roche limit, the planet's immense gravity, its tidal forces, overwhelms the moon's own gravity. The planet begins to stretch the moon, and then, in a display of incredible cosmic violence, it tears the moon apart. The moon is shattered. Its icy crust, its rocky mantle, and its hot metallic core are all ripped to pieces. These fragments are then scattered. Most will fall into the planet or be captured in a ring, but some thrown by the gravitational slingshot could be ejected from their home solar system, entirely sent to wander the dark, cold vacuum of the galaxy for millions of years. This theory is compelling because it explains the data that the comet theory struggles with. First, it would explain the visitor's solid, dense structure and its rocky-looking surface. It was not a fluffy comet, it was a piece of rock. Second, it perfectly explains the presence of metals like nickel. The nickel was not a strange gassy compound. It was a literal chip from the shattered moon's metallic core. This is a much simpler way to explain the nickel sighting. It also might explain the object's strange rotation. The violent process of being torn apart could easily have sent the fragments spinning in a complex, tumbling way. This exomoon theory is a champion of the discontinuity camp. It is still a natural process, but it suggests a source for interstellar object shattered moons that we had never seriously considered before. It paints a picture of the galaxy as a place of incredible casual violence, where the debris of broken worlds is constantly being exchanged between stars. Between these two major theories, the debate rages. But there are other ideas, ones that exist on the fringes of the discussion. Theory number 3 is a subtle but important one, the primordial rogue planetesimal. This idea is different from both the comet and the moon theory. Both of those objects were born inside a solar system formed around a parent star. This theory suggests the visitor was born alone in the vast, freezing cold molecular cloud between the stars. The galaxy is full of these enormous clouds of gas and dust. They are the great stellar nurseries, the places where new stars and their solar systems are born. The standard thinking is that planets and comets form after a star is born from the leftover disk of material surrounding it. This theory, however, suggests that in the deepest, coldest parts of these clouds, planetesimals, small kilometer-sized bodies of rock and ice, could form directly from the cloud's raw material. They would never be part of a solar system. They would be true orphans from birth, true wanderers. If this were true, it would explain why the visitor's chemistry was so strange. It would not be made of the processed materials of a solar system, which have been heated, mixed, and sorted by a star. Instead, it would be made of the raw, unprocessed, primitive materials of the interstellar cloud itself. This could explain the strange mix of carbon compounds and the lack of water. This theory is fringe not because it is physically impossible, but because it is very difficult to test. It suggests a whole new population of objects that we have not yet accounted for. Finally, we arrive at theory number 4, the one that is the most famous, the most controversial, and the most exciting, the provocative hypothesis of an artificial origin. This is the idea most famously championed by Harvard astronomer Avi Loeb. Let us be absolutely clear, there is zero direct evidence for this theory. We have no photograph of a spaceship. We detected no radio signals. We have no definitive technosignature. This theory is for almost all scientists the very last, least likely and most fantastic possibility. So why do we even talk about it? Because of the logical argument Loeb puts forward. He looks at the pile of contradictory data, the acceleration with no tail, the strange shape, the weird composition, and he sees a scientific community twisting itself in knots to find a natural explanation. The carbon-rich comet theory, for example, requires a very specific never-before-seen object. The exomoon theory requires a specific violent event. Loeb's argument is this: we are so determined to find a natural cause that we are suffering from confirmation bias. We assume it must be natural. But what if he asks we are simply looking at the data with our prejudices? What if the object's acceleration was not from invisible gas jets, but from a light sail? A very thin, very large and very lightweight piece of technology designed to be pushed by the pressure of starlight itself. A light sail would accelerate exactly as the object did with no tail and no gas. This is an extraordinary claim, and in science extraordinary claims require extraordinary evidence. Loeb does not have that evidence. Instead, he is making a philosophical point. He is challenging the scientific community's reluctance to even consider the possibility of extraterrestrial intelligence. His theory is less of a scientific hypothesis and more of a what-if that pokes at our biases. It is a provocation in the truest sense of the word. While 99.9% of scientists believe the object was natural, Loeb's idea serves a purpose. It forces the mainstream theories to be better. It raises the stakes. If you want to prove the light sail theory wrong, you must come up with a natural theory that is better and simpler at explaining all the facts. In this way, even the most out-there theory can be a valuable part of the scientific process. This brings us to the most important part of the entire story, the nature of the debate itself. This whole controversy, this messy, passionate, and very public argument is a perfect illustration of science happening in real time. Science is not what you see in movies with a lone genius in a lab, having a sudden eureka moment and writing the answer on a chalkboard. Real science is a human process. It is chaotic. It is full of arguments, egos, and stubbornness. It is about people dedicating their lives to a set of ideas and defending them. When the Division for Planetary Sciences (DPS) held a major meeting to discuss the visitor, the atmosphere was electric. Scientists from the Comet camp presented their models. Scientists from the Moon camp presented theirs. Data was challenged. Interpretations were attacked. New contradictory observations were presented. It was messy, it was confusing, and it was absolutely beautiful. This is how knowledge is made. It is a battle of ideas where the only judge is the evidence. Right now, the evidence is not good enough to declare a winner. The data we have is being reanalyzed, reinterpreted, and looked at from new angles. Each theory forces its rivals to be more rigorous. This controversy is not a sign that science is broken, it is a sign that science is working. It is the sound of the engine of discovery, an engine that is fueled by the one thing this mysterious visitor gave us in abundance, a profound, beautiful, and world-changing mystery. The answer is still out there waiting. We have travelled so very far on this journey, following the faint ghostly trail of 3i Atlas as it fell through our solar system and vanished once more into the deep. We have looked at the evidence, we have weighed the theories, and now, as our exploration comes to a close, we must ask the most important question: what did it all mean? Perhaps the greatest lesson of 3i Atlas is not what it told us about it, but what it told us about us. This visitor, this fragment of another star's family, was never really a visitor at all. It was a mirror. It held a reflection up to humanity, and what we saw staring back was our own deep-seated Earth-centric bias. We saw a shape we did not immediately understand, and so we wanted it to be a starship. We saw behaviour we could not explain, and so we wanted it to be intelligent. We were in effect looking for ourselves out there in the dark. 3i Atlas simply showed us that our definitions of normal are built on a sample size of our own solar system. We assumed all comets were like our comets. We assumed all chemical processes were like our chemical processes. The universe, it seems, has little interest in our assumptions. And this leads us to the second and perhaps more hopeful metaphor, the metaphor of potential. If this object teaches us anything, it is that the cosmos is far more diverse, more strange, and more chemically creative than we ever dared to imagine. The building blocks are everywhere. We see the mists of acetylene holding the potential for dicarbon. We see the fine dust of nickel holding the potential for exotic carbonyls. The universe is a vast cosmic laboratory running countless experiments in parallel under conditions we have never seen and can barely simulate. It suggests that the seeds of life, or at least the complex chemistry that precedes life, might be astonishingly common. But it also comes with a warning. It warns us that this chemistry may not look anything like our own. It may not be based on liquid water. It may not produce the things we recognize. It may be built from chemical pathways that are to our eyes utterly and profoundly alien. The universe is not just stranger than we imagine, it is stranger than we can imagine. This visitor, 3I Atlas and Oumuamua, before it were just the beginning. They were the first few drops of rain that signal a coming storm. But humanity is no longer standing by simply waiting to be surprised. We are preparing. On a remote mountaintop in Chile, the Vera Rubin Observatory is preparing to open its enormous eye. When it begins its decade-long survey of the sky, it will not find one or two of these interstellar travelers. Scientists estimate it will find 20, perhaps even 50, every single year. The trickle is about to become a flood. We will have a catalogue, and we will not just be watching them fly by. The European Space Agency has a clever craft called the Comet Interceptor already built, currently waiting patiently in the cold of space at a stable location known as Lagrange Point 2. It is a sentinel dormant, just waiting for the next pristine visitor to cross into our territory, a visitor on a path we can finally reach. When that target is spotted, the interceptor will fire its engines and fly to meet it. It will taste its dust and analyze its gases up close. Looking further ahead into the 2030s, NASA is deep in the planning stages for a mission called the Interstellar Probe. This craft would be a true hunter. It would be designed from the ground up to be the fastest object humanity has ever built, with the specific thrilling goal of chasing down one of these objects and flying alongside it as it leaves our sun behind, capturing data all the way. We will not be caught by surprise again. We are ready for the next chapter. So as we settle in, let us take one final peaceful breath and close the loops on the mystery of 3I Atlas. Let us put all the questions to rest. That haunting, beautiful blue-green glow that so captured our imagination we found its source. It was not an alien engine. It was the simple natural chemistry of dicarbon released from acetylene ice as the sun's warmth finally touched it. It was a process we see in our own comets, just fueled by a different, more exotic ice. The mystery of the nickel. The strange metallic signature that seemed so out of place. It was not the hull of a derelict ship. It was nickel carbonyl gas, a compound that forms naturally though rarely when carbon monoxide gas meets metallic nickel dust. It was a chemical process, not an industrial one. And what of its strange gentle push, the non-gravitational acceleration that seemed to defy our models? It was not a hidden drive. It was the object itself breathing. It was the gentle, sustained pressure of all those different ices, nitrogen, carbon monoxide, acetylene, all turning to gas at different times in different places on its surface. It was a multi-volatile sublimation, a complex gentle outgassing that nudged it along its path, its origin. Not some distant advanced empire, but a metal-rich star system. A place where the planetary nursery included more metallic dust than our own, leading to a comet born with a nickel-rich core, a natural though different birthplace. When we look at all the evidence, piece by piece the puzzle comes together. And the picture it creates is one of nature. There is no evidence, not one single shred, that 3 Atlas was artificial. It was a messenger, but not a sentient one. The true meaning of 3I Atlas is that we are changing. We are as a species learning to read these new messages from the cosmos. For all of human history, we have been limited to studying our own small neighbourhood. Our astronomy was solar astronomy. Now for the first time we are holding pieces of other star systems in our hands, or at least in the data of our telescopes. We are doing interstellar astronomy. This is not the end of a story, it is the very, very beginning of one. We have finally opened the door to the galaxy. If this journey has helped you relax or wonder or see the night sky in a new way, we hope you will join our crew. You can show your support by liking this video and subscribing for more journeys into the cosmos. We have a question for you to ponder as you drift off. If we find the next interstellar visitor, what should we name it? Oumuamua meant scout. Atlas was a giant. What should the next name be? Let us know your ideas in the comments below. Join us next time as we ask an even bigger question. We have now received 2 messengers from the stars. Perhaps it is time we sent a message back. We will explore the challenges, the dangers, and the profound hope of sending a reply to the stars. Until then, rest well. Rest well.